Located in the 90th place on the periodic table is the element thorium. Thorium, as with every element, has unique properties, making it useful in certain applications. However, thorium's best days still might be ahead of it, and it might move itself to the front of the list of the world's most important elements. Learn more about thorium, how it was discovered, and its potential uses on this episode of Everything Everywhere Daily. This episode is sponsored by ButcherBox. One of the things I like best about ButcherBox is figuring out all the different ways to prepare the products I get. Cooking a steak can be pretty straightforward, although I'm going to begin experimenting with the sous vide method of cooking, doing what's known as a reverse sear. It's supposedly the best way to cook a steak, and a worthy method of preparation for the high-quality steaks you get from ButcherBox. I also received some ground beef in my last shipment, and made what I've called a meat donut. Instead of pressing the ground beef into patties, I molded it into the shape of a donut, fried it, and then I cooked an egg in the center of the donut. It was actually great. If you would like to try the meat donut, you are in luck, because ButcherBox is now offering free ground beef for a year. Receive 2 pounds of ground beef for a year and get $20 off your first box when you sign up today at butcherbox.com/daily and use code DAILY. Once again, that's butcherbox.com/daily, promo code DAILY.
Quentin here runs a sustainable clothing brand.
Hi there.
He's excited that his shipping company FedEx has set a goal of having carbon-neutral operations by 2040.
Impressive.
When an influencer tweeted about his recycled bamboo t-shirts, Quentin unexpectedly became quite popular.
I'll take it.
He uses FedEx to reach new customers around the globe, while making Earth a priority. FedEx, where now meets next.
The story of thorium begins in 1815 at the Falun copper mine in Sweden. Falun at the time was the most productive copper mine in the world, and copper from the mine had been the single biggest export from Sweden over the previous several centuries. A previously unknown mineral had been discovered, and it was given to the chemist Jöns Jacob Berzelius to determine what it was. Berzelius had previously discovered the elements cerium and selenium. After analyzing the substance in 1817, he determined that he had once again discovered a new element. He called the new element thorium after the ancient Norse god of thunder, Thor. However, Berzelius got it wrong. It wasn't a new element, it was actually yttrium orthophosphate. Fast forward to 1828. An amateur Norwegian mineralogist by the name of Morten Thron Esmark found an unusual mineral in Telemark, Norway. He sent it to his father, who was a professor of geology. He couldn't figure out what it was, so he sent it to Berzelius. Berzelius analyzed the substance and concluded that this was in fact a new element. And this time, the new element was now going to be called thorium. And this time he got it right. It was a new element, and the mineral it was found in was dubbed thorite. For decades after its discovery, there was no practical use found for thorium. It wasn't until 1885 that it found its first and biggest use as a mantle for gas lamps. For those of you old enough, you might remember seeing mantles in gas camping lanterns. They looked like mesh bags that would shine brightly when heated with a gas flame. They were in fact mesh cloth bags which were impregnated with thorium oxide, a substance with a very high melting point. When the gas mantles were lit, the cloth part would burn away, leaving a very fragile mesh of thorium oxide which would glow brightly. In 1898, probably the most important attribute of thorium was discovered. Both the German chemist Gerhard Karl Schmidt and the Polish-born Marie Curie discovered that thorium was radioactive. This was the second element which was discovered to have this property after uranium, which was discovered 2 years earlier. The next year, the New Zealand physicist Ernest Rutherford and the American electrical engineer Robert Bowie Owens were studying thorium and found some very confusing results. It appeared that the radioactivity of thorium could vary dramatically. What they found was that one of the elements that thorium decayed into was present. It was a radioactive gas that was dubbed radon, a new element. It was the study of thorium which led to the discovery of half-lives and solidified the theory that radiation was the decay of elements. Thorium was found to be weakly radioactive. The half-life of thorium was determined to be 14.05 billion years. And to put that into perspective, the age of the universe is believed to only be 13.7 billion years old. If you remember back to my previous episode on radiation, the shorter the half-life of something is, the more radioactive it is. It is, to use a metaphor, burning up faster. When I was in Boy Scouts, we would use gas lanterns, and we were always told that the mantles were radioactive. And technically, that was true. There was thorium in the mantles, and thorium is radioactive. Over the last 30 years, the use of thorium in gas mantles has been phased out because the delicate mesh which is created can easily turn to ash where it can be breathed in. While thorium is usually quite safe, it can be dangerous if ingested or inhaled. They have subsequently been replaced by mantles made of substances like yttrium, which don't glow as brightly, but also don't contain thorium. With the phase-out of gas mantles, there are almost no other industrial or commercial uses of thorium. The end. Wait, I forgot there is one other potential use for thorium. Thorium could possibly provide clean and almost unlimited energy for the entire world. Yeah, you heard me right. Currently, all of the active nuclear power plants in the world use uranium as their power source. If you remember back to my episode on uranium, there are two naturally occurring isotopes of uranium, U-238 and U-235. 99.3% of all uranium is U-238, and only 0.7% is U-235. Uranium-235, however, has the special property of being fissile. A fissile isotope has the ability to sustain a chain reaction using nuclear fission. It emits somewhere between 2.5 to 3 neutrons when it is hit by a neutron. Those neutrons hit other fissile isotopes, which release more isotopes, and so on and so on. U-238 is what's known as a fertile isotope. When it is hit with a neutron, it can undergo a series of decays to become plutonium-239, which is then a fissile material. Plutonium-239 and uranium-235 are the most common fissile materials used in nuclear reactors and in nuclear weapons. The process of separating uranium-235 from uranium-238 is known as enrichment, and it is an incredibly expensive and slow process. The vast majority of money spent during the Manhattan Project, for example, was spent in separating U-235 or creating plutonium-239. What does thorium have to do with any of this? Thorium only has one naturally occurring isotope, thorium-232. There are no fissile versions of thorium that exist. However, thorium-232, like uranium-238, is fertile, meaning if you hit it with a neutron, it can be turned into something which is fissile. In the case of thorium-232, when it captures a neutron, it turns into thorium-233, which is very unstable. This undergoes a beta decay where a neutron spits out an electron to become a proton. This turns thorium-233 into protactinium-233. Protactinium-233 is likewise unstable and undergoes another beta decay to create uranium-233. In my previous episode on uranium, I never mentioned uranium-233 because it doesn't exist in nature. For all practical purposes, it isn't used for anything. However, uranium-233 is fissile, just like uranium-235, and it's part of the thorium cycle. So, when thorium captures a neutron, it sets off a series of events resulting in uranium-233, which gives off neutrons, which allows for a chain reaction. Reactors which use fertile isotopes to create fissile isotopes are known as breeder reactors. Long story short, you can use thorium for nuclear power. Moreover, there are a whole bunch of benefits to using thorium over using uranium for nuclear reactors. For starters, thorium is much more abundant. There is about 3 to 4 times as much thorium on Earth as there is uranium. As I mentioned above, thorium has no real applications or use. Thorium ore is usually just a byproduct of mining other rare earth elements. Ore with large amounts of thorium is just left behind in slag heaps. Moreover, you don't need to enrich thorium because there's only one isotope. Another big benefit a thorium reactor has over a uranium reactor is that it is almost impossible to make nuclear weapons from it. Modern reactors create plutonium-239, the primary fuel for nuclear weapons. This wasn't considered a bug in the design of these reactors, it was at the time considered a feature. The ability to create plutonium that could be used in weapons was considered a side benefit during the Cold War. A thorium reactor does not create plutonium-239. In theory, it is possible to make a weapon from uranium-233, but both the Americans and the Soviets experimented with this and found it far too difficult to be practical. So in terms of nuclear proliferation, it would be easier to build a bomb from scratch than it would be to try and use uranium-233. However, it gets even better. One particular type of reactor that's been suggested not only uses thorium, but also uses a liquid salt rather than a solid as the fuel source. This type of reactor is known as a liquid fluoride thorium reactor, or LFTR, or LIFTR for short. The proposed fuel would be a salt made out of lithium fluoride and beryllium fluoride. The mixture is known by the great acronym FLIBE. FLIBE would serve as both a coolant for the reactor, but also as a solvent for the nuclear material. FLIBE has a much higher melting and boiling point, which means that you could run a reactor with much lower pressures than with water. Water in conventional nuclear reactors is one of its most dangerous aspects. At the exceptionally high temperatures found in nuclear reactors, water becomes a steam with very high pressure. Think a pressure cooker on steroids. This high pressure is the reason why containment facilities are needed in most nuclear reactors, to prevent the catastrophic release of high-pressured steam. A LIFTR is considered a high-temperature reactor. A solvent like FLIBE would just be a very hot liquid, not a gas under high pressure. Moreover, a liquid fuel source can be consumed more completely than a solid fuel source, resulting in less waste. And not only would there be less waste, but the waste that comes out of a thorium reactor would be about 1,000 times less radioactive than what comes out of a conventional nuclear reactor. There's a lot to be said about the subject of nuclear waste, but I will save that for a future episode. On top of all these benefits, a molten salt reactor can have built-in inherent safety mechanisms that would kick in even if all the machinery were turned off and all the humans disappeared. In the event of overheating, plugs made of solid salt would melt, allowing the liquid to drain away into a tank where moderators would stop the chain reaction. The only thing required in a thorium reactor is some sort of neutron emitter to kickstart the process. And where can you get that? From the current nuclear waste that's sitting around. So, if thorium reactors are so great, why weren't thorium reactors developed? Well, it turns out there have been advocates for thorium reactors as long as there has been nuclear power. There was a period back in the 50s and 60s where most nuclear scientists just assumed that thorium reactors, or at least breeder reactors, were going to be the future because they made so much sense. The United States went down the path of using uranium-based reactors in the 1950s due to the knowledge gained during the Manhattan Project. We simply knew more about uranium than we did about thorium at that time. There have been experimental thorium reactors that have been built. In 1962, a thorium reactor was built at the Indian Point Energy Center just outside of New York City. The Oak Ridge National Laboratory built the molten salt reactor experiment. It went critical in 1965 and ran until 1969, and used thorium in a molten salt as its fuel source, and it ran for over 15,000 hours producing energy. Development of uranium reactors continued both because of institutional inertia and because plutonium was needed for the production of nuclear weapons. In 1973, the United States stopped all research into thorium reactors. Alvin Weinberg, head of the Oak Ridge National Labs, which is the largest nuclear research and development center in the United States, was fired in 1974 because he championed the development of safer thorium reactors. Within a matter of years, it was entirely possible to get a PhD in nuclear engineering and never once encounter the thorium reaction chain. There has been a revival of interest in thorium power given all of its benefits. Several atomic agencies around the world have conducted experiments with thorium reactors or have recently announced their interest to do so. China has begun tests on thorium reactors, and India has probably shown the biggest interest in thorium as they have the world's largest thorium reserves and very little uranium. There has also been renewed bipartisan interest in the United States Congress to revive thorium reactor research. There have been several startup companies who are looking to create thorium-based reactors and small modular reactors based on thorium. In previous episodes about various elements, I've mentioned the role that they've played in history and how they've contributed to the modern world. In the case of thorium, it has played almost no part in the modern world and has had almost no historical impact. But that may be about to change. Thorium may be thrust into the spotlight, going from one of the most useless elements to one of the most important elements for the future of humanity. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Thor, Thomsen, and Peter Bennett. Today's review comes from listener Autumn Vine 101 from Apple Podcasts in South Africa. They write, "Great for young and old. This is a great informative podcast. We as a family with teens learn so much while listening to the short episodes, even on our current road trip through a part of our beautiful country, South Africa. We all love this informal way of getting to know more about the world and far-off places. We differ from you in many of our aspects in our view of the world and history, but find that there's more to learn this way as it opens our mind to different viewpoints and points of view. Our constant companions are atlases, roadmaps, a globe, timelines, and history books." Autumn Vine 101 from the Heidelberg Basin, South Africa. Thank you, Autumn Vine. I'm glad to hear you're enjoying the show with your kids, and your country is indeed beautiful. I've had the pleasure of visiting every state in South Africa, and I've enjoyed all of it. From Kimberley to Kruger, Cape Town, Johannesburg, Soweto, Durban, Port Elizabeth, and Bloemfontein. I've even taken the Blue Train from Cape Town to Pretoria, and it is indeed a great place for a road trip. Remember, if you leave a review or send me a boostagram, you too can have it read on the show.